So in this section of Chapter 7, we will talk about collisions in 1 dimensions and 2 dimensions. So what is a collision? In a collision, two objects exert forces on each other or for a very small interval of time. Hence, we can separate the motion into three basic parts: before the collision, after the collision, and during the collision. So in order to define what these three sections are, we assume that the objects are far apart in such a way that they don't exert forces on each other before and after the collision. During the collision, the forces are exerted according to Newton's third law. They are equal in magnitude and opposite in direction, and they act on two different objects. These forces are also assumed to be larger than any external environmental forces that are acting during that time. So, in a nutshell, collision is a brief interaction between two or more objects. We use the word collision when the interaction time is very short relative to the entire motion. During a collision, objects exert forces which are equal and opposite on one another. So let's say you have mass m1 and mass m2 and they're both coming in. They will exert a force on each other for a very short interval of time, and these forces will be internal forces. And then they will go away from each other and that interaction. And we can ignore all the forces when we compare the velocities just before and just after the collision. Billiard balls hitting each other are a classic example which is applicable in the science of collision detection. So if I was to take an example, if there are no external forces present, then the total momentum is conserved. So the initial momentum, two masses coming in with velocities v1 and v2. Final momentum, they go away from each other, v1 and v2, with the possible exception of the change in angle. So by the total momentum conservation, we mean p1i plus p2i equals p1f plus p2f. So this is a vector equation. So basically what that means is we have to find, if we have a collision in, say, 2 dimensions, we can't just simply add those two vectors up, but we have to find components in both of these coordinates. So very simply, before the collision, the sum of initial momentums is equals to the sum of collisions after the momentum. And during the collision, there will be a slight impact force that if the objects are elastic, they will change shape, but then they will go back to their original shapes once they move away from each other. And the forces that are acting on them are going to be equal in magnitudes and opposite in direction. So initial and final velocities in various two-body situations are shown here. So if mass of the object 1 is much larger than mass of object 2, and they're coming in with about the same magnitude of velocities, what will happen is that after the collision, most of the mass 1 will slow down and mass 2 will actually speed up. If the situation was that m1 and m2 are coming in with velocities v1 and v2 and they stick together after the collision, then the final velocity going away will be one velocity that goes away. For a case of a head-on collision, if mass 1, which is the bigger one, carries the bigger velocity and mass 2 is the one that carries the smaller velocity, there will be hardly any impact change in the velocities of mass 1, but velocity of mass 2 will increase. The last situation is the inelastic collision when they both stick together. M1 coming in, M2 going in, they stick together, they will finally move away with the same velocity going out. So there are basically 3 kinds of collisions that we will deal with. One of them is called an elastic collision. Elastic collision is where both colliding objects do not change their shapes. The total linear momentum is conserved and total kinetic energy is conserved. Inelastic collision is that the shape of one or both of the objects changes during the collision. The total linear momentum is still conserved. However, total kinetic energy is not conserved. Completely inelastic collision means that the colliding objects stick together after their collision. Total momentum is still conserved in the system. However, the kinetic energy is not. So an example of an elastic collision is in which both momentum and kinetic energies are conserved. There is no dissipative force like friction that is present during the collision, and all of the kinetic energy of the objects before is still the same as the kinetic energy afterwards. So for macroscopic objects which come into contact in a collision, there's always some dissipation, and they are never perfectly elastic. Collisions between hard steel ball, as those in this apparatus, are nearly elastic collisions. Collision in ideal gases are very nearly elastic, and this fact is used in development of expressions for gas pressure and container. So not only the collisions within the molecules are elastic, but collisions with the walls of the container are also are completely elastic. So for an elastic collision in one dimension, the momentum is conserved and is given by m1 v1 plus m2 v2 equals m1 v1 final plus m2 v2 final. In one dimension, the velocity is represented by positive or negative numbers to indicate directions. Kinetic energy is also conserved, which is given by this formula here. Kinetic energy is initials equals kinetic energy finals. We can solve for two variables if the other four are known. Another useful result for elastic collision is that the magnitude of the relative velocity is the same before and after the collision. So for a case where we have a stationary target, if m1 is equals to m2, then v1f will be 0, and the entire the velocity will be converted to the second mass for the target mass, and the target mass will attain all of the initial velocity. If m1 is much smaller than m2, then the incident particle will recoil in the opposite direction and will transfer some of its momentum and velocity to the particle 2. If m1 is much larger than m2, then both particles will still move forward after the collision, except that the target will gain a lot of velocity and the incident particle will not lose too much. And you can see this in this animation. So note, m1 comes in with initial velocity v, and m2 goes away with the final velocity. So for a head-on collision, if you have a head-on collision, one coming with v velocity and the other one going with a half a velocity, on their way out, if you notice, the first one will go away with v by 2, and the other one will go with a velocity v. So it's basically a velocity exchange. Both moving in the same direction. If the black one carries a velocity v and m2 is carrying the half the velocity, then the velocity gets transferred and they still move in the same direction. So I'm going to pause here for a minute while you look at all of these three animations and see how the velocity gets transferred. Note, during elastic collision, both kinetic energy as well as momentum should be conserved. In the limiting cases, if m1 is much smaller than m2, then the incident particle will rebound with nearly its original speed and nothing will happen to the target. If m1 is much greater than the target velocity, as the case here, you see a big mass coming and colliding with a little mass. The little mass will go away with twice the velocity, almost, and there will be not much change in the initial velocity, as it is seen here. Right, so 2m comes in with velocity v, m goes away, and 2m recoils back. Right? Now, an inelastic collision is a collision in which the kinetic energy is not conserved. In collision of macroscopic bodies, for example, these both will stick together, and this will be called a completely inelastic collision. Okay? A collision between an electron and a positron in a detector would look something like this: an electron and a positron coming in, and the energy is being converted into the formation of other particles. Now here's a question that you should ask yourself. A small compact car and a large truck collide head-on with each other and stick together. So this is an example of which kind of collision? Elastic or inelastic? Which undergoes the large magnitude momentum change? The car, the truck, or is it the same for both, or can't tell without knowing the final velocity of the wreck? Interesting. The magnitude of the momentum change will be exactly the same as we saw in the example that we did before. Why? Because the forces that are acting on them are equal, even though they may be opposite, but the magnitude of their forces is the same. So now which goes the large magnitude acceleration during the collision? The car, the truck, or is it the same for both, or can't tell without knowing the final velocity of the wreck? Now think about it for a second. Now we're talking about accelerations. Which will have the largest acceleration? Of course the car, right? Because it has a smaller mass, and since the momentum change is the same for both of them, so the effect on the smaller car will be more.